Mm, I've already apologised to Max for plagiarising his presentation, but I was struck when Max gave his presentation uh, earlier that he sort of in passing mentioned this device, the Z-Match tuner. Sorry, the Z-Match matching unit, because you can't make a non-resonant antenna resonant, as I keep trying to impress upon people. And I will also start the clock here, by the way. And I decided to look at it and try, because it's largely been passed by. We're so used to now pressing the button and the auto tuner taking over, and it's a sort of skill and art, really. It is matching. Let's just run through a bit of what Max was talking about to refresh your memory. And I didn't realise that Clever Max animates some of his stuff and it moves about. So he talked about a typical approach of multiband long wire, 9-to-1 or none, lossy ground. Whoop, there we go. Too clever for me, this. And this is all right. You can pay 40 quid and buy a piece of wire and an unknown for 40 meters, but or 20 meters, but it's the wrong length for any other band, really. And in a typical long wire system, you've got ground currents, invisible capacitors, and the height above ground is important for your wire antenna. You've got lossy ground, especially if you're in a car park doing a POTA. You can run a counterpoise. It's not a radial if it's on the ground, it's a counterpoise. All right. But the long wire has issues. It's unbalanced if it's fed by coax through an impedance transformer. It's roughly average for the feed point, typically assumed to be 450 ohms on the other side of the transformer, but 50 ohms on your side where your transmitter is. That's its purpose. The true feed point impedance varies depending on the band because, as we all know, impedance isn't static like resistance. It could exceed 1.5K with complex reactive components. Big words, man. You got to remember I'm a Sun reader. Right, the unknown can't cope with reactive loads. No impedance transformer can. So there are frequencies where the SWR and the coax feed line may exceed 10-to-1 after the unknown. This is typically what happens with your G5RV, which Louis Varney G5RV told me it exists because they're the only bits he had in Brazil. Ground loss returns are high. Coax losses can be high in high common mode current. In other words, it's a bag of trouble. You're not getting the best out of your system doing this. And then Max produced some maths. Maths. Hello, come in. You're in detention. Yeah, and he was showing here the length of the antenna, was it? Are you showing the impedance here? That's showing the... Yeah, that's a half wave. Yeah. That's a half wave. We'll not dwell on this because I don't understand it. Well, there was a lot of writing there, you see, a lot of graphs work and stuff that I was asleep in that lesson at school. But this is not really what we're here to talk about. We're here to talk about ladder lines. Now, I couldn't resist this photograph. I love irony. Is this a ladder looking for a line, or is he stealing the ladder? I think it's wonderful. It's worth a caption. Ladder line or balance line, which is the better technical term and that's a ladder line. Now, when I was a lad, BC, before coax, all the amateurs I knew used this and made this, and you can make your own with strips of plastic. This is a ladder line on speed. Is this? It's the king of ladder lines. Fantastic. You can actually buy these spreaders. This looks like commercial spreader actually with this little thing here, and the width between the lines controls the impedance. Let's not get harmonica related over the lengths facts. He's looking over my shoulder all the time. But so ladder line was very, very popular. Now today commercially, that would typically be somewhere have an impedance of 600 to 800 ohms. If I can get past this, I'm probably out of focus, which is a good thing. That is 300 ohm ladder line. Typically you buy 350 or 450 ladder line, and I learned a good tips from Max is that to stop it wearing, was it you twist it? One twist per foot is what it needs to do. But of course we've now got a high impedance line here, which is way beyond the capabilities of your magic push the button instant tune and forget. And this is tradition. Your first photo's coming in a minute, John. This is tradition. That says transceiver, but I grew up with transmitters. Coax. What's missing from this is a SWR meter, a VSWR, because we're looking. You only get 50 ohms from there to there, and this is a variable frequency transformer, matching the ladder line. Max was saying that you don't make the legs of a doublet resonant length, because if you multiply 3.5 to 7, in other words 80 to 40 meters, and then looked at it, they're not exact matches, and the same applies the higher you go. With a dipole here, and it goes out of sync, in other words, it's no longer the same. It becomes a half wave or 2 half waves or whatever. So the thing changes. The beauty of the ladder line over the coax, of course, is that it's called balanced line, and we don't get any radiation. If you've got a mismatch on an antenna, there are 3 currents flowing in a piece of coax, and this is why we use a balancing device there, or we'll put ferrite chokes on, because you've got the center current, you've got the inside of the outer braid, and you've got the outside of the braid as well. And it's the current on the outside of the outer braid, say that right, that causes your interference and your RF burns when you pick the microphone up. Right, so this is what we're looking to do. Balanced line has a low ground loss, low return loss. There's a lot to be said for using a balanced line, especially, by the way, if you're on a PME earthing system. Well, that's for another night. Higher feeder impedances lower the SWR at the feed point, reduces the SWR losses. The doublet or the double ZEP. The double ZEP named after the Zeppelin, where they actually they only use half of it on the hydrogen-filled Zeppelins. Line losses with coax and parallel feed lines. Where's the line losses, Max?
dB.
Yeah. Where's the worst one?
You're looking at 69 to 1 SWR.
Yeah.
5.368 megahertz.
Flipping heck. What's that one then? 10.8? 10.8? Oh, yeah. But this is your standing wave ratio, and you can see it. Oh, yeah, there it is. Yeah. You can see it changing all the time. Oh, you've been animating again, haven't you? Oh, he's at it again. Oh, yes. Now, I didn't need to ask you because you've done it. This is the beggar of using somebody else's work. Right, 130 feet So 140 feet is best if you have the room and want the strongest results on 80 meters. Do you really need the strongest results on 80 meters to listen to the infirmary net? You only need it for the contest. 90 to 110 works, second best on 80 meters. 65 to 75. You see, that 66 feet is a resonant length. It's just off that 66 feet to give you the best. The downside, right? Okay. It requires a symmetrical installation. If you alter the symmetry, in other words, one leg up, one leg down, nearer the earth, whatever, you get a problem. Balanced line must be kept straight and perpendicular to the antenna. Open wire balanced line should be kept out of reach to avoid the risk of shocks, RF burns, next door's cat, unless you don't like next door's cat. Absolutely. Right, okay. It's a compromise. But if you can only get one antenna up, you need to be able to match it. And this is a picture that attracted my attention in the first instance. And this is an SCM Z match. We're going to go into the Z match in detail, and that's really why we're here. You can draw this circuit in a number of different ways. Just make a note of this little extra inductor with the switch on, which I'll come back to in a little while when we see the practical side of this. And that you've got one input and two outputs. There's an even later model than that, Max. Right, okay, so where does it all begin? Oh, you're at it again. Note he doesn't call it a tuner. Antenna matching unit, please remember. Look, these type of matching devices offer the lowest losses for an unbalanced, a balanced or an unbalanced output. Actually, don't rely on a coax tuner's internal balance, because you will see tuner units and they have a meaty great balun and a couple of terminals on the back. Right, you can find yourself just warming it up and losing a lot. Like autotuners, wideband balance give you something reasonable. Right, this is the first Z match antenna that I ever used. You notice there's no switch, there's no band operating, just two controls on the front. And what you do is when you set the thing up with your antenna, you make a note of these dial positions for each band, and that's where it all begins. It's a very simple, very simple but very cunning device. That's the inside of it, and that's all there is. But there's a lot going on in here. This is a differential capacitor called a butterfly. That's a more normal capacitor. These coils are interesting. In fact, you can just see, I should have taken a sideways picture, but I couldn't find the one I'd already done. There are two coils here because it's a transformer. There's an inner and an outer wound on these coils. I tried to get an answer today before I left from the KW group as to who made those coils. I think they were imported from America from a company called Air Ducts. And the way you wind those coils is very interesting, because you wind them on a slightly smaller mandrel than you actually want, so that when you put them over, you put these plastic, if you like, plastic devices. When you put them over, they want to reform back inwards. Then you pass a current through the wire and just melt it slightly in and solidify it. It's a labor-intensive process. And you have to kind of like set up proper jigs to make it. I've got some here for you to pass around, but they're a different type, and I'll come to those later. Nearly made my first mistake. Right, okay. This capacitor is taking the output straight from the transmitter. and you actually have 2 tuner units based on this. Right, okay. But those coils, you used to be able to buy them by the yard. And this is from the back of a 1961 ARR manual, and it's export department in New York, cable address, New York, Canadian rep, and they're Sunnyvale, California. They're not made anymore. You will find coils like this on eBay from time to time, and if I see them, I buy them, because you can't get it. And if you see them, particularly in a longish length, they're fantastic for making tuner units and all sorts of messing about. They're very handy for things like the base of a vertical. The feed impedance to ground is very low, but if you add some inductance, you raise the feed point to your coax level. They're good for that, and you could literally buy them. The diameters, I mean, they must have had a factory making them. You got all different diameters, all different wire gauges, and I think KW imported them to make their devices. So I'm not going backwards, I am going forwards. So that's what's inside the Z match, basically. But like everything else, hello, we don't need this, we've had this. Pardon? Yeah, yeah. There we go. You happy now, John? Yeah. Right. This, back in 1960s, when I started, everybody had separate transmitters. This is not a transceiver, it's a transmitter. It's part of my vintage collection, Sado that I am. And as I said before, the transmitters didn't have auto tune matches in them. You had, look at that, that is a VSWR bridge and a half, isn't it? But it is 75 ohms as well. So there we have what we said before: transmitter, inline, and your Z match. And then you can put virtually any kind of antenna you like on the end of it. I make no apologies for the next gratuitous photograph, because it's one that I am actually quite proud of. 10 years later, we're on to transceivers. That is one of only 3 that ever existed. I had the privilege of having that for some work and repairs on it in my shack secretly for 2 years and didn't tell anybody. It's in the RSGB collection at Bletchley. It is the personal radio of Rolly Shear's JKW. But we're into transceivers. We've got station monitors. We've got kilowatt linear, and our tuner unit, our basic 2 capacitor 2 coil unit, has grown. Now you know that you can buy a bit. The manufacturer brings out a Fiat 500. I can see one through the window, and then he has a deluxe model and the add-on model, and then he has the Monte Carlo, and then he has the and the price goes up. Once you've sold all the basic models, you need to get more money out of it. But because we had a separate box before, but it's now inside here. If we take a closer look at it, but I used that station and loved it. It's still there. It's still there. Look. We've now got our VSWR bridge and power meter in there. Nice big meter, more for your money. And we've now gained an antenna switch. And the antenna switch we've also got 2 inputs now, because by the 70s and 80s, people had their long wire or their doublet, and they had maybe a dipole for one single monobander, and then maybe have a 3-band antenna, a vertical, or indeed if you were a plutocrat, you had a 100-foot tower and a Yagi. So they've grown, but it's still the same basic device inside. This is the back of that one. That incidentally is I'll just go back. That is a 109. You put a bigger number on it, it handles more power. They're the same capacitors inside, but the 107 is the most popular, but the 109. was supposedly the high power, the deluxe, the Monte Carlo version. When KW finished in '79, it was sold to Decca, and Decca carried on and made things like the Decca Cat and other things, which by this time were full of Plessy ICs. And they continued, but they stuck a Decca label over it. So you'll see some with a Decca label. They changed the case to square, to a square case with sharp corners. And when they were fed up with it, because by this time we were beginning to see the stirrings of the autotuner, auto matcher, which of course with little microprocessors referencing VSWR and everything, and coax line antennas becoming very, very popular, they got rid of it. They sold off the parts and the part builds and everything, just like your DeLorean cars. Take it as it comes. And they sold those off to SMC. Hands up who remembers SMC? Or am I still too? Oh, no, I'm not quite old enough yet. Right. Okay. South Midlands Communications on the water in Hampshire, and they stuck an SMC label over it until they ran out of parts. So that's the history of that Z-Match. And that's the back of it. And you can see the single input from the transceiver, the two antennas, and still the balance. But there's nothing changed inside. There's no great ferrite or anything in there. It's still the same thing. This is a balanced output, and we notice there's a ground there because you can actually put a wire on one side and then tune a long wire with it, because the impedance transformation available from a Z-Match is so great. If we go back to what we sort of touched on earlier, and those high impedances, this will cope with it. So you've got the best of both worlds. You can use balanced or unbalanced. Now, if you notice, we've got two different outputs like there was on that circuit diagram there. And there's a very good reason for that. Whoops. This is how it works, notionally, for the layman. Now, I could go into all sorts of transmission line theory about generators and terminal load resistors, you know, like the national grid at this end and the overhead pylons and the substation transformer. It's the same idea. You've got to match the load to what's being generated. The Z-Match is two tuner units in one. It's very clever. It comes initially from the original design is the tank circuit of a valve transmitter way back, BC, before coax, because the outputs of transmitters, either low or high power, were fed into balanced lines, and that's how it works. I said there were two outputs on the thing, and there they are. What happens here, if I've got this right, this is one circuit. This is that single capacitor that I showed you, and this is the very clever butterfly capacitor that's at the heart of it. They are opposed in the sense that when one is fully meshed, the other one is open. Right, okay. Here is one of the last butterfly capacitors in captivity. All made by Jackson. Can't buy them now. If you wanted that, making would cost you over £100. You can buy a whole Z-Match for 80 quid on eBay, and it's a travesty. Between 80 and 150 quid. And just be careful with the vanes, please, because I haven't got any more. And you can clearly see that one's meshed and one. If you just like to pass that around and let people see it. Right, what's happening here is that, let's take this capacitor here and this. We're forming a tuned circuit here, fed by this. We've got a tuned circuit operating here, and it's all down to what frequency we're pumping in from here. This is, if you like, anti-resonant. It's at minimum. It's not really there. This piece of wire and this and this small coil, because it is a much smaller coil, is basically like a long lead to that capacitor. But at this time, if we change what we're putting in here down to say 21 megahertz, this capacitor is almost out of circuit. This is anti-resonant, so it sees this as a low impedance feed. Similarly, when that's out, it sees this as a low impedance that it can match to, and there's your output. Now this capacitor is floating. That capacitor is floating. This is virtual earth potential. I find this circuit a lot easier to understand than the way it was drawn on the previous diagram. And that's the basics of how it works. That's a slightly different arrangement of the two. Yeah, when this is working, that's virtually earth potential. It's very clever, and it's a very old and it's a unique design. Now enter Paul Crapper. Anybody ever heard of Paul Crapper? It is nothing to do with what you think. Paul Crapper was a very unusual character that lived in a place called Solid, and he had a company called Solid State Modules. Solid is a hamlet of no more than 5 houses. It's now a cul-de-sac off the road to Penistone, just outside the town centre. And Paul manufactured and traded under the name of Solid State Modules until I think it was either a trading like offence or it was the tax man. I'm not sure which it is. Paul, when I used to visit Paul in this Georgian fronted house, he was chain smoking, and you could cut it with a knife when you went in. There was a bottle of scotch and an ashtray full of cigarettes. But he was clever. And he was even more clever because he didn't make anything. He farmed it out to all the amateurs in Huddersfield to make for him. And it was like the Cragvale coiners. There were people everywhere making bits, chassis bashing, circuit making, etc., etc. And it was in the days of crystal controlled VHF G8 having 2 meters only, having 2 meters only, or 77s only, sorry, to start with, and then 2 meters only. And there was a boom. Transistor front ends and new Vista front ends weren't that sensitive, and he made a lot of money with. He bought a lot of food and bottles with this VHF preamplifier. Originally, it was just a circuit board, and then he put relays in both ends and an RF sensing mechanism, and of course it switched from transmit to receive. He moved on from there. Now I couldn't get a decent picture of this, remembering the original FT101. The original FT101 transceiver, which revolutionized amateur radio, the Yaesu. And he made a transverter from 28 megahertz to 2 meters, and he made a 4 meter one. It had a QQVO640 in the PA, right? And it plugged into the accessory socket, and it was an absolute game changer for all these burgeoning G8s who were robbing World War II bombers for SCR 322s and everything, A-line radars just to get bits. It got red hot. There was no fans. It worked. I'm sorry, this is a terrible photograph, but it's the only one I could find online. I borrowed one of these for the expedition, and it was absolutely fantastic. And that's when I really came to know Paul and his wife Susan. This is the last Z match that he started to make. The Z match. These Z matches were all built in Cleckheaton in a terrace house by Mike G4 EZV, and Mike became my business partner in Northern Communications and Communications Products Limited, and he became the service director of my company. and he was well, he is a lovely man and a bit of a recluse, very quiet guy, and he built virtually every one. And just like I showed you, coming from the basics, just two capacitors, two sets of coils, it grew. It grew direct tuner. There's that nasty word again. Direct via the matching unit, a dummy load, top band. Now you have to remember that I said I pointed to a little switch and a little coil. I'll show you that in a minute. 160 meters, we were allowed 10 watts of RF or 28 watts PP. This was full power, 400 or 500 watts. The matching of a Z match to the antenna is very precise. It's not like your broadband balun, and it's a bit like, to get used to it, it's a bit like doing this, which I can't do. And it grew and grew just like the other one, but it didn't obviously have a VSWR bridge in it, because we'd reached the point where transceivers were having those. And I suggested to Paul, he'd upgraded it and upgraded it. I suggested to Paul, I said, you're selling to a lot of shortwave listeners, aren't you? Because see, this thing will work all the way from 1 to 30 megs. And a lot of shortwave listeners, yeah. I said, well, the only way the shortwave listener can get it somewhere near a match for the antenna is listening for the noise coming up. And it's a bit of a black art. Why don't you put a noise bridge in it? Noise bridge, I wanted to bring a couple of noise bridges, but I couldn't find them. I'd first seen those in America by Omega Bridge, and then the Cambridge in this country, and the DIY version. It's a transistorized circuit that you need to power, and it comes up with a noise signal, and courtesy of our old friend Mr. Wheatstone and his bridge, you null it out so that the bridge is balanced, and what starts as a loud hissing goes down to zero. So there's no energy going into it, no power from a transmitter required. What it also does, where's that capacitor got to? All right. It's not in your pocket, is it? Right. The distance between the vanes and the capacitor are quite small because they were really Jackson receiving capacitors. Now, if you try and offload one of these things, it's not on resonance. You'll get RF flashover, and I've seen quite a lot of second-hand ones with RF flashover. And you develop a pip on one plate and a little tiny dent or a hole, and you can short circuit a whole vane very easily on a capacitor. So this was a boon for the transmitters as well, because they could get if they couldn't, if they'd lost the back of the fag packet, which had the numbers on, you could do it. And that's it. These slow motion dials, by the way, the KW1 had an internal. These slow motion dials were imported from Japan. They're Eagle products. Brought them into the country. You cannot buy them; they're no longer made. What am I bid for this? They were a round about a fiver when people earned 16 shillings a week. You'd be lucky on eBay to get one under 30 quid, 30 or 40 pounds. Sky's the limit. I've only got the one, which is annoying. But they're a lovely thing. I'm sure that some of the older members will be familiar with them. Yeah. But you don't see them today. So going back to what I said before, you can pay £100 for your capacitors. You can pay another 60, 70 quid for these. A Z match on eBay is beginning to look extremely good value for money. Another gratuitous photograph, this FTDX, never used for transmitting, one careful owner, is for sale. Thought I'd get the adverts in halfway through. Right. This is the inside of Paul's last Z match. He started with two separate coils. It's really Mike's Z match, and it's what I was just been talking about. Here's your capacitor. Here's your two coils. Originally, when he made them, it's in a much smaller box. It's not as deep. because transceivers are getting smaller. And Mike came up with this idea. He could put them all on one board, and if they're at 90 degrees to each other, he didn't get any interaction. What you must, in a Z match, you can get harmonic relations between your two coils, and in the design, you must avoid that in the design. So came up with this printed circuit board. Now you can no longer get these airlux coils. So Mike came up with another brilliant solution, which was to use a printed circuit board. Back to that little switch, top bound 10 watts, Mike came up with an idea to cut 2 slots in there and shove a piece of drain pipe in and add some more inductance. If you look closely at this one, it's melted. It's melted because the switch on the back of the KW transceiver was low power, and when you were on top band at night and the television had finished transmitting, it used to accidentally get switched or forgotten about. There is, just go back. He's added a dummy load. This is a cheap way, not a big carbon rod. This is a cheap way to make but it fits the space. There's the band switch, plastic band switch, but I've never seen, Mike said he'd never seen one melted, just this top band coil. He used to get a lot of money from repairs, and he was nipping off to the hardware shop for lengths of rain tubing. There it is. Now you can clearly see out of focus, if you can. These two coils, one inside the other. Here is the noise bridge. Again, with those relays, those flat pack relays that I said switch between receive and transmit. Sensors. There's a RF diode switch in there. Although it does tell you to turn it off, you will still fry your transistors. And this is how the basis of a noise bridge operates. There's a ZD1 noise generating diode. That's, if you notice, a little hook on there. And we're amplifying this signal and feeding it into this. Oh, we now have toroids. And we have the two legs of our, this is one side or two parts of our Wheatstone bridge. Here is the two, say, detector and what does that say on the other one? Unknown, right. So that's your antenna. That's your antenna. And once you get this balanced, you've got, once you balance this, you can actually calibrate the dial with a range of impedances. So it predates things obviously like our VNAs, and you can actually get a sense of the impedance of the coax that you're feeding with this thing. But it's quite a simple circuit. So just to round that up, that's the history of the Z match as far as that's concerned. Bullet points, versatile, unique design, balanced and unbalanced matching in one box. Very simple, wide impedance range, up to 5,000 ohms, which we talked about the off center, not off center, the off resonance antennas, and of course it adds additional selectivity to the front end of your receiver once you get the thing on tune. So from there, let's have a look at them. I've got them here, all the things you've seen, and here they are to look at. Here is the original Z match. There it is. Here is just shove it out of the way. And okay, right, what's that? Oh, I knew that screwdriver there. Okay, just to round off these talks, here is a KW109. What's that? Oh, this is a Z match. Beloved of QRP is built from a kit. There they are. There's your two capacitors. It can switch in some additional inductance, and this one has a VSWR bridge in which operates on a light, dim light or dimming light. And here is Paul's Z match, or should be Mike's Z match. And there they are, for you to look at. The coils that I mentioned, again, the last one's not in captivity, made, they're held in place, they're soldered. Big coil, little coil. Big coil for you, and a little coil for you, and when they get to there, I'll have them back. Okay, so that, ladies and gentlemen, at some length, is the Z match. Thank you.
We really appreciate you taking the time to watch this video. Don't forget to check the video description where you'll find additional information about the video you've just watched, along with links to products used and to the Haddai's website. If you enjoyed this presentation, please feel free to hit that like button. Maybe you'd also consider subscribing and clicking the notification bell so we can let you know the next time we release another video. Thanks again for watching.